Section 6.3 Polar Forms and Area. Up to now, the only coordinate system we have used is the Cartesian coordinate system. In this section, we introduce the polar coordinate system. The contents of this section is as follows. First, we define the polar coordinate system. Then, we study graphs in the polar coordinate system. Next, we learn how to find the intersection of polar curves. Finally, we study formulas to find the area in the polar form curves. The polar coordinate system. In the polar coordinate system, points are plotted in relation to a fixed point O called the origin, or pole, and a fixed ray emanating from the origin called the polar axis. In the polar coordinate system, points are plotted in relation to a fixed point O called the origin or pole, and a fixed ray emanating from the origin called the polar axis. We then associate it with each point P in the plane an ordered pair of numbers P, R, theta, where R is the distance from O to P and theta is the angle measured from the polar axis to the ray OP. The number R is called the radial coordinate of P, and theta is the polar angle. The polar angle The number R is called the radial coordinate of P, and theta is the polar angle. The polar angle is considered positive if measured counterclockwise from the polar axis, and negative if measured clockwise. There is a simple trigonometry relationship linking polar and rectangular coordinates. If we assume that the origin of the rectangular coordinate system is the pole, and the positive x-axis is the polar axis, then the rectangular coordinates xy of each point are related to the polar coordinates r theta of the same point by the formula summarized in the box. To change from polar to rectangular form, we use the formula x equals r cosine theta, y equals r sine theta. To change from rectangular to polar form, we use the formula r equals square root of x squared plus y squared, and the inverse tangent of and theta equals the inverse tangent of y divided by x. Note that to find theta, we also have to find which quadrants it lies by noting the signs of x and y. We take an example. Locate the point with the given polar coordinates in the plane. A, 2 pi over 4. B, 2 minus pi over 4. C, 2 5 pi over 4. And D, 2 minus pi over 4. To locate point A, first we rotate counterclockwise and draw a ray from O that makes an angle of pi over 4 with the polar axis. The point A is located in this ray so that the distance OA is 2. To locate point B, first we rotate counterclockwise. To locate point B, first we rotate clockwise and draw a ray from O that makes an angle of pi over 4 with the polar axis. The point B is located in this ray so that the distance OB is 2. To locate point C, first we rotate counterclockwise and draw a ray from O that makes an angle of 5 pi over 4 with the polar axis. The point C is located in this ray so that the distance OC is 2. To locate point D, first we rotate clockwise and draw a ray from O that makes an angle of pi over 4 with the polar axis. Since the radial coordinate is negative, the point D is located on the opposite of this ray, so that the distance OD is 2. There is some notice relating the polar coordinates. Where each point in the plane associated with exactly one pair of rectangular coordinates, a given point in polar coordinates has an infinite number of representations. For example, square root of a pi over 4 minus square root of a 5 pi over 4 and square root of a 9 pi over 4 all represent the same point in polar coordinates. The non-uniqueness of representation in the polar coordinate system causes some difficulties, but this can be handled by exercising a little care. Next, the origin O has polar coordinates 0, theta for all angles theta. Polar graphs. The graph of an equation in polar coordinates is the set of all points P whose polar coordinates are theta satisfy the given equation. For example, graph the equation r equals 3. The graph is the set of all points r theta such that the first component is 3 for any angle theta. This is a circle with radius 3, center at the origin. Now, graph the equation theta equals pi over 4. The graph is the set of all polar points r theta with polar angle theta equals pi over 4. This is a line through the origin on the point that makes an angle pi over 4 with the polar. This is a line through the origin on the point that makes an angle pi over 4 with the positive x-axis. We consider another example, graph r equals theta. We start from theta equals 0, then r equals 0. This point is the pole. When theta increases, r increases accordingly. Starting from the pole, it will rotate counterclockwise. The distance to the point is increasing. The graph of this equation is a spiral. Graph r equals 4 cosine theta. We construct a table of values by choosing values for theta and approximating the corresponding values for r. Do not forget that even though we pick theta and find a value for r, we still represent the table values as other pair of the form r theta. Then we plot the corresponding points in the plane. When theta equals 0, r equals 0, the first point is at the pole. When theta equals pi over 2, r equals 4, we obtain the second point. When theta equals pi, r equals 0, the third point is also at the pole. When theta equals 3 pi over 4, when theta equals 3 pi over 2, r equals minus 4, we obtain the fourth point. The points are connected and we obtain a circle. Graph the equation r equals 2 multiplied by 1 minus cosine theta. We construct a table of values of r theta and plot the corresponding points in the plane. When theta is 0, r is 0. The first point is at the pole. When theta equals pi over 2, r equals 2, we obtain the second point. When theta equals pi, r equals 4, we obtain the third point. When theta equals 3 pi over 2, r equals 2, we obtain the fourth point. The points are connected and we obtain a cardioid. This is a special case of a more general curve called limaçon. Graph the equation of a limaçon r equals 1 minus 2 cosine theta. We construct a table of values of r theta and plot the corresponding points in the plane. When theta equals 0, r equals minus 1, we obtain the first point. When theta equals pi over 2, r equals 1, we obtain the second point. When theta equals 3, when theta equals pi, r equals 3, we obtain the third point. When theta equals 3 pi over 2, r equals 1, we obtain the fourth point. In fact, a limason will be like this. So, there must be additional points between theta equals 0 and theta equals pi over 2. We create another table for values of theta between 0 and pi over 2. When theta equals pi over 4, r equals 1 minus square root of 2, we obtain the point 1 prime. When theta equals pi over 4, r equals 1 minus square root of 2, we obtain the point 1 prime. When theta equals pi over 3, r equals 0, we obtain the point 1 prime prime. Now, there are enough points to sketch the graph. We obtain the graph of the given limason. In the following example, we will graph the rose curve r equals 4 cosine of 2 theta. We construct a table of values of r theta, for theta a multiple of pi over 4, and plot the corresponding points in the plane. The points are plotted as follows. The first point, the second point is the pole, the third point, the fourth point is the pole, the fifth point, the sixth point is the pole, the seventh point, the eighth point is the pole. Connecting the points by order, we obtain a rose curve with 4 petals. In the following example, we will graph the lemniscate r squared equals 4 cosine of 2 theta. We construct a table of values of r theta, for theta a multiple of pi over 4, and plot the corresponding points in the plane. The points are plotted as follows. The first point, the second point is the pole, the third point is undefined, the fourth point is the pole, the fifth point, the sixth point is the pole, the seventh point is undefined, the eighth point is the pole. Connecting the points by order, we obtain a lemniscate. The black zone is the zone where r is not defined. Intersection of polar form curves. In polar coordinates, one point has more than one representation, so the method for finding intersection of polar form curves will include sketching the graphs. Step 1. Find all simultaneous solutions of the given systems of equations. Step 2. Determine whether the point r equals 0 lies on the two graphs. Step 3. Graph the curves to look for other points of intersection. We consider an example. Find the points of intersection of the curves r equals 3 seconds minus cosine theta and theta equals 2 pi over 3. First, we solve the system by substituting theta equals 2 pi over 3 in the equation. We obtain r equals 2. So the intersection point, we obtain r equals 2. So the first intersection point is 2 pi over 3. Then we check if the pole lies on the two graphs. Substituting r equals 0, we see that cosine theta equals 3 seconds, so the point is not an intersection point. Finally, by sketching the graphs, we found another intersection point. The coordinate of this point is found by adding pi to the angle theta, 2 pi over 3, to obtain r equal 1. This point has another coordinate. The coordinate of this point is found by adding pi to the angle theta, 2 pi over 3. So theta equals 5 pi over 3. Substituting this value in the first equation, we obtain r equals 1. This point has another coordinate, minus 1, 2 pi over 3. Polar area. To find the area of a region bounded by a polar graph, we use Riemann sums in such the same way as when we developed the integral formula for the area of a region described in rectangular form. However, instead of using rectangular area as the basic unit, in polar form we sum areas of circular sectors. Then we take the sum of the area of these circular sectors. When the number of circular sectors become large, we get closer to the exact value. This value is defined by a limit. The area of a circular sector of radius r is given by r squared multiplied by 1/2 of delta theta, where theta is the central angle of the sector measured in radians. To remember this formula, just think of a circle as a circular sector with central angle of 2 pi. Using the formula for the area of a sector, we now state a theorem that gives us a formula for finding the area enclosed by a polar curve. Let r equal f theta define a polar curve where f is continuous and f theta greater than or equal to 0 on the closed interval alpha to beta, where 0 is less than or equal to beta minus alpha is less than or equal to 2 pi. Then the region bounded by the curve r equal f theta and the rays theta equal alpha and theta equal beta has area a equal 1/2 of the integral from alpha to beta of f theta squared d theta. Find the area of one leaf of r equal 4 cosine 2 theta. We will probably find that the most difficult part of the problem is defined. You will probably find that the most difficult part of the problem is deciding on the limits of integration. A sketch of the region will help with this. One leaf is shown in the figure. Theta goes from minus pi over 4 to pi over 4. The Riemann sum of the area is sigma of 1/2 multiplied by 4 cosine of 2 theta k star squared multiplied by delta theta k. So the area is given by the integral from minus pi over 4 to pi over 4. 1/2 multiplied by 4 cosine 2 theta squared d theta. The resulting integral is simplified as the integral of 8 cosine squared 2 theta d theta. Using the half angle identities gives cosine squared 2 theta is written as 1/2 of 1 plus cosine 4 theta. Simplify the integral and calculate, we obtain 4 multiplied by theta plus 1/4 of sine 4 theta. Substituting the limits gives the result 2 pi. In the following example, we find the area enclosed by two curves, r equal to sine theta and r equal to cosine theta. First, we graph and find the intersection by solving the equation 2 sine theta equal to cosine theta. It implies tangent of theta equals 1, which results in theta equal pi over 4 or 5 over 4, and r equals square root of 2 or minus square root of 2. By looking at the graph, we see that the pole is another point of intersection. So keep in mind that graphing is extremely important in polar coordinates. The given area must be divided into two parts. The first part contains a part of a curve r equal to sine theta. The endpoints correspond to theta equals 0 and theta equals pi over 4. The area of this part is the integral from 0 to pi over 4 of 1/2 multiplied by 2 sine theta squared. The second part contains a part of a curve r equal to cosine theta. The endpoints correspond to theta equal pi over 4 and theta equal pi over 2. The area of this part is the integral from pi over 4 to pi over 2, 1/2 of 2 cosine theta squared. We end this section by the following example. Find the area outside the limit case r equal to square root of cosine 2 theta and inside the circle r equal 3 cosine theta. The given area is the difference between the area of the circle and the area of the limit case. The area of the circle is found by the integral from minus pi over 2 to pi over 2 of 1/2 multiplied by 3 cosine theta squared. The limits of integration is found by graphing and using the equation r equal 3 cosine theta. The area of the limit case is found by the integral from minus pi over 4 to pi over 4 of 1/2 multiplied by 2 square root of cosine 2 theta squared. The limits of integration is found by graphing and using the equation r equal to square root of cosine 2 theta. You may find that the solution is quite lengthy when we need to find the right limits of the integral in the above example. But remember that this is different from finding the area between two curves in rectangular coordinates, and we cannot use the formula the integral of 1/2 of 3 cosine theta minus 2 square root of cosine 2 theta squared, which is equals to the outer curve minus the inner curve. You may find that the solution is quite lengthy when we need to find the right limits of the integral in the above examples. But remember that this is different from finding the area between two curves in rectangular coordinates, so we cannot use the formula. The integral of 1/2 of 3 cosine theta minus 2 square root of cosine 2 theta squared. This is the end of section 6.3. Thanks for watching.